Air from the environment enters through the nostrils, goes through the airways, and finally reaches the alveoli, which are the tiny air-filled sacs in the lungs. Here, gases exchange between the alveoli and the blood flowing through the capillaries that surround each alveolus. And blood flows from the higher pressured arteriole to the lower pressured venule. Now, P big A, which is the pressure within the alveoli of the lungs, is relatively constant throughout the lungs. At the end of expiration, it's equal to atmospheric pressure, which is 0 centimeters of water. And although the pressure in the arterioles is greater than the pressure in the venules, their values change at different vertical levels within the lungs. Consider the fact that some blood vessels are more vertical while others are more horizontal. The horizontal ones are unaffected by gravity, but the more vertical ones are affected by gravity. The analogy would be a cylinder filled with water. The cylinder represents a blood vessel and the water would be the blood. As you add more and more water, the height of the water increases. And when the column is completely filled, the pressure from the water that's exerted on the bottom of the cylinder, or hydrostatic pressure, is equal to the density of the water multiplied by gravitational acceleration, multiplied by the height of the column of water above it. Blood in vertical blood vessels in upright lungs have similar hydrostatic effects. At the apex of the lung, pressure in the arterioles and venules are relatively low. At the base of the lung, pressure in the arterioles and venules are relatively high. And in the middle of the lung, the pressures are somewhere in between. Now, because the pressure in the alveoli is constant, the relationship of the pressure in the arterioles and the venules with respect to the pressure in the alveoli changes. And it's the relationship between these three that determines the zones of the lungs. In zone 3, at the base of the lungs, pressure in the arterioles is higher than in the venules, but both are higher than the pressure in the alveoli. In zone 3, blood flows through the capillaries because of the pressure difference between pressure in the arterioles and pressure in the venules. Now, even though the pressure in the arterioles and venules exceeds the pressure in one adjacent alveoli, the protein and cells that make up the walls of the alveoli are strong enough to resist collapsing. In zone 2, in the middle to top, or apex of the lungs, pressure in the arterioles is higher than pressure in the alveoli, but pressure in the alveoli is higher than the pressure in the venules. In zone 2, as before, blood flows through the capillaries because of the pressure difference between the pressure in the arterioles and the venules. And also as before, the alveoli don't get crushed even though they're at higher pressure in the nearby arterioles. Now, here the alveolar pressure is greater than the venule pressure, and the blood vessels feel the pressure directly because they share a basement membrane with the alveoli. This causes the venules to get slightly crushed, decreasing their diameter, and increasing their resistance, which leads to a decrease in blood flowing through them. But arteriolar blood continues to flow into the venule, overcoming that external pressure. It's kind of like a clothespin pinching down a bit on a straw. If you blow air into one end of the straw, the clothespin will make it harder for air to get through the other side. But if there's enough pressure, then the air will overcome the resistance and make it through. In zone 1, at the extreme apex of the lungs, pressure in the alveoli is higher than pressure in the arterioles, which is still higher than pressure in the venules. In this zone, blood does not flow because the arterioles get crushed by the relatively higher pressures in the nearby alveoli. Now, normally, the structure of blood vessels and alveoli allow them to resist completely collapsing. So this only happens in non-physiologic conditions, like when pressure in the arterioles decreases drastically, like during a hemorrhage, or when pressure in the alveoli increases drastically, like during positive pressure ventilation. During these times, the pressure in the alveoli can crush the capillaries and completely cut off blood flow, creating dead space. Alright, as a quick recap. Pulmonary blood flow through the 4 zones of the lungs is unequal, and it's driven by the effects of pressure gradients in blood vessels as well as the pressure within alveoli. In zone 3, in decreasing order, there's pressure in the arterioles, then pressure in the venules, and then pressure in alveoli. In zone 2, pressure in the arterioles, then pressure in alveoli, and then pressure in the venules. In zone 1, at the extreme apex, which normally doesn't happen under physiologic conditions, you have pressure in alveoli, then pressure in arterioles, then pressure in the venules.